Hello everyone. We are moving towards circuits now, so this is our first circuits question. We've got a question posed as we want to find the resistance at T2 given the resistance at T1 and alpha of T0. And we're also given T0 for alpha. So first thing we should notice is when we FOIL this out, we get something linear in terms of t. T0 is a constant, so we get this. R of t equals R0 plus R0 alpha times t minus R0 alpha T0. And I'm going to move this over in terms of just t, so we get R of t is equal to R0 minus R0 alpha T0 plus R0 alpha t. So what we see here is actually that the slope of this line is R0 alpha, and the rest of it doesn't actually amount to anything other than a constant. So our interrogation of this has been pretty fruitful. We found out an important fact about this, which is that it's only linear in terms of t. Okay, so as we move on, we need to keep in mind that R0 is playing into this still. So let's solve for R of T2. We've got R of T2 is equal to R0 times 1 plus alpha times T minus T0. So to start, we want to find R0 to move forward with the problem. So we get that, going back to the original equation, we have R of T0 is equal to R0 is equal to R0 plus 0. Yeah. So this is pretty self-explanatory. R of T1 we need to solve for in terms of R0 is equal to R0 times 1 plus alpha times T minus T0. Now here is the key. For T1, which is not equal to T2, we're solving for T1 to get R0. So what we want here is that R of T1, which we're given, over 1 plus alpha, which we're given, times T minus T0, which we're given, is equal to R0. So what we want to solve for is that linear slope term. Right? If we just skip ahead and say R of T2 is equal to R of T1 times 1 minus alpha T minus T0, well then what we're doing here is we're actually assuming that this term is, this T0 is T1, which is not the case. So what we want to go back to, and what we want to solve for in terms of, I'm going to erase that so we don't get confused, right? We want to solve for R0. We want to start this problem by solving for R0, which is right here. Okay. So, now that we have R0, then we plug in T2 to our equation for resistance. And let's actually use the term for R0 so we can see what the algebra looks like to do it in one step. Okay, so this implies that R of T2 is equal to R of T1 over 1 plus alpha T1 minus T0, right, times 1 plus alpha T2 minus T0, which is distinctly not the same as putting this in terms of R of T1. So, to write that really big, I'll write it really big, then I'll circle it, and we'll move on. Okay, so we've got this just in an algebraic equation. We've solved for the term we're looking for. Now, let's think about another couple interesting facts about this resistance equation before we move on. Right, so we've got R of t is equal to R naught, that's all that stuff. Now, when we look at this, of course it's linear in terms of R naught alpha. That's the slope of this. We get something that's just a straight line graph, right? So here would be R naught. And as we move up, the rise over the run is equal to R naught alpha t. Okay. So this is the key to the actual graphing of this. But what can that tell us about this? Well, so what does this equation look like? This equation looks like the equation for thermal expansion. If you have been in Physics 211, you did a small section on thermal expansion as well. And it should have been something like this. Which is identical. It is an identical formula. Now, with that being the case, we can actually say that these are related because of the atoms in the material. If you look at what materials have different conductance and different resistance and things like that, it's pretty much one-to-one tied to their thermal qualities as well, because it has to do with valence electrons and the band gap, which I don't think that you will learn in this class, but it's touched on in Chemistry 1, for those of you who are pre-med, bio, nursing, etc., chemistry, obviously. Okay.